This is Miss Green, and today we're going to do 7-4A. Whoops, sometimes it just does that. Okay, 7-4A, graphing the sine and cosine functions. So we're going to graph these functions and notice some things about them and compare them, and just a few other things we're going to figure out about the graphs of these functions. So you will need a graphing device of some sort. I would like you to look at, and I apologize, this didn't come up very well when I transferred it. If you can look at these different graphs, these are all modeling something in the real world. And I'll reread this. I'll read this for you. So what I was wanting for the first one was to match the graph that would show a woman walking at a steady rate of 2 miles per hour. Which one of these graphs? Which one of the graphs would show a ball falling from a cliff when measuring the distance versus the time? And then the last one is, which one would show the amount of money earned when it's invested into a savings account and it's compounded, let's say, at a yearly rate? Which one of these would show that? If you need to stop and then come back, that's fine. You may know off the top of your head. So when I'm looking for a steady rate of change, I go to the linear one, the line. Steady rate of change. So the rate of the slope is always the same through the whole thing. This would be a linear function. When I think about something accelerating as it falls, I would use this graph right here. And you might remember that from some of your physics. But this is telling me that as it falls, it's going to fall at a faster rate. So here I have varying rates of change. So from here to here, the rate of change would be different than from here to here. See how steep that slope is. So when I have that kind of situation with this kind of environment, this would be parabolic or parabola, which is a quadratic function. And I'm doing this to show you that the reason we have these different math models is so that we can predict what's going to happen to certain things in the real world, whether it be money, a ball, or somebody walking or driving a car. We like to make predictions of what could happen or what did happen. Now, when I have money invested and it's compounded, we know that this would give us an exponential function like this. And hopefully you remember that we used the inverse of that, the logarithmic functions, to help us solve some of those exponential functions. Today we're going to look at this trig function graph. So here's something I got it off the internet, but it's showing what a sine function looks like. The sine of x. So you can see some things about it that might be kind of interesting. When you do this on your calculator, to get the same periods, as we call it, you need to set the mode to radians. Otherwise, you won't get this graph to look like this. So the x is in radians is what it's telling us when I do the sine of x. X is in radians. Then you might want to change your window. If it's any larger, you won't be able, it'll look kind of like this and you can't really see the waves. So you'll want to do that. I would like you to tell me what you notice about the graph. And you can write some of these things down. If you're in class with me, I'll ask you some questions about what you did notice. You see how this part is in black? Goes up down and back up again. And then right here, it seems to repeat that pattern. So that's one thing you may notice, that there's a repeating pattern. You may also notice that it never gets any higher than this, no matter how often it repeats it, and it never gets any lower than this number right here for the y. So this is -1, and this is +1 up here. There's also a line that's halfway between the maximum and the minimum. All those things, we're going to give names to them. So you'll want to take some notes here on the next page. We're going to define these items. And I apologize too, that looks like my, it doesn't show you all of this, but these types of functions are used to represent repeating motions. And this could be measuring a pendulum and how far it is from its starting point where it's just facing down. And this would be a perfect wave if there were no friction. It would be perfect like this all the time. It would be the same height each time. Or you could think about the orbit of, this is the Earth around the sun, but the orbit of any planet would work as far as something that happens over and over. Here's our definitions. This type of function that's repeating is called a periodic function because a pattern is repeated, and that repetition of the first one, that x value right there, that's called the period. And then you repeat it again over another 2 pi, whatever x is, time or whatever it is. And then it's always repeated. Every 2 pi on the x-axis, this pattern is repeated. So the 2 pi is the period for this particular function. And this function is my sine wave. It's called a wave because it kind of looks like a wave. So this is my sine function, and the period is always 2 pi. Now what this is saying, that it's 2 pi, I can take any value of x, and 2 pi later I'll have the same value of x. I'll have the same y value for that x. So for instance, at pi, say x is pi, then 2 pi later, at 3 pi, I'll have the same y value, 0. Pi 0, 3 pi 0. I know that sounds kind of weird because we don't, you could think in your head if it makes more sense, 3.14 pi, 3.140, and then this would be 9.42 if I did it fast and quickly enough. Again, if I looked at pi over 2 right here, I would get a value of 1. So if I add 2 pi to that, so pi over 2 plus 2 pi, that would give me 5 pi over 2, right? 2.5. I also get a value of 1. So that's what this means right here. It looks a little odd. When you see that repeating function, just think of the word periodic function. I'm going to go to a new word on the next page. This maximum and minimum, you're familiar with those already. That would be your y max and your y min. The line that's halfway between them is called the midline. So this is the horizontal line that's halfway between the min and max values is called the midline. Notice the midline for the sine function is the x-axis. And notice we haven't shifted anything up or down. This is just the plain old sine function. F of x equals sine of x. Now look at this right here. From this maximum point to that midline is called my amplitude. Notice it only goes to 1. The sine of x equals 1. When x is, we talked about this a little while ago, x is pi over 2. So when x is pi over 2, the sine of pi over 2 is 1. So that's the maximum it can get. Now you could also do right here So this would be 1.5 pi's or 3 pi over 2. That still would have an amplitude of 1, even though that value is -1. The amplitude is a distance, so it's always the absolute value of my y. So just remember that it's always must be positive. And you can't read this again because of the way the screen is, but this says that there is a maximum minimum height, and we call that the amplitude, but I'm just repeating the height being the distance to the midline. I'm repeating that. What are some other key features of the graph of y equals sine of x? Well, let's look at that. I don't know if you see anything else that stands out to you. And I talked about this just a little bit. So the maximum and minimum. So the maximum, it starts here at pi over 2, and then you can just add 2 pi. K just changes. So if I add 2 pi once, I would get here. I add 2 pi again, so I'd multiply it 2 pi times 2, so I'd add 4 pi to that. Then you would just 1, 2, 3, 4, 1, 2, 3, 4. You go here, right? And then, so this would be the maximums. That's the maximum. And then notice the minimum starts at 3 pi over 2, 1.5. There's the 1.5 going down like this. And then again, because the period is 2 pi, I can go to another, add 2 pi to that. And I know some of that looks a little fancy, and you're like, I have never seen anything like that on the screen, but don't worry about it. Those are just some things you could notice from that. Now, you also might take a look at the domain. Like many of our functions, the domain is all real numbers, right? This is all real numbers. Here's what I like to do for all real numbers. And do you notice that there are infinitely many zeros occurring at every multiple of pi? So at pi and 2 pi and 3 pi and 4 pi, it's kind of interesting. When x is all of those, the y is 0. So that's kind of just an interesting observation. Another thing we might want to look at is the range. Because I have a min and max, and it's included, I use the bracket, that's also my range. You should be getting pretty good at those domains and ranges by now. The graph of y equals sine of x has a midline at y equals 0. That's my x-axis. Sometimes we flip that around, but notice this goes through y equals 0. And every point on here would have 0 as the y value. So that's why y equals 0. And it has an amplitude of 1. And this is true for this function right here. So the midline, the domain, the range, the amplitude, and we didn't have it on here, but if you remember, the period was 2 pi. It's kind of written into that right there. Period is 2 pi. Now, what I would like you to do is go ahead and graph the cosine of x and try to fill in all these things. This other one down here says the maximum occurs at, so go ahead and try to fill that in and then come back when you have it done. So the period again is 2 pi, and the amplitude's the same as the sine, and so is the midline, the domain, and the range. The only thing that's different is where the minimum and the maximum occur. So if you did it properly, you'd notice that cosine actually has a maximum. It starts at 0, and then of course, since the period, sorry, it's not perfect. Since the period is 2 pi, the next one will be right here where this is 2 pi. Now your calculator probably doesn't come up with pi, but you would know 2 pi would be a little more than 6. So if you count 1, 2, 3, 4, 5, 6, and a little more, you would see where that peak is. So the 6 would be about right here, the 6 marking. Now, the minimum, the first one and in the positive, is right here. So we could start on pi, and then we would add 2 pi to that however many times. So we would go way over here. We can't even see it. Whoops. And then that would be where the next minimum would occur. Again, try to, as best you can, wrap your head around this, but this one's pretty straightforward from looking at the graph. Now, if I want to do some things to that cosine graph, so say I want to multiply it by 3. Whatever my y value is here on the cosine of x, I'm going to multiply it by 3. Well, you can imagine what's going to happen to the graph, right? You can imagine that if this is the blue one, that's my cosine of y, and then the orange one is my 3 times. You can see that for every output here was 1, so I multiply that by 3, and then I would get an output of 3 here. And the same thing here for the minimum. This was -1, right? We knew that. So the output would go down to -3. But of course, 3 times 0 is 0. So these don't change. It doesn't look like the period changed, does it? Definitely the amplitude changed. So I would like you to think about and look at the two graphs and compare which features are the same. So we just said the period is the same. You could say the midline, that doesn't change. And think about range and domain. Well, wait a minute, the range does change, right? So that wouldn't work, but the domain is still all real numbers. So we think about which of the features are different. Well, I just said range, and the reason the range changed is because the min and max changed. Well, these all deal with the y values, so that means my amplitude must have also changed. These all relate to the y values, and notice I multiplied 3 times what my initial y value was. All right, let's look at the next thing. Now, if we graph, now we're going to change the x before we do the function. So we have the blue is the sine of x, and the red one is I'm multiplying x by 2 and then taking the sine of that. That one looks a little different, right? Looks like I shrunk it together a little bit. I made the waves closer together. That means it's affecting the period. So when initially the period was from, if you remember, it was 2 pi, right? So 6 something, right? So initially the blue one, it was 2 pi. But now I actually have a period. If I start here at 0, next time it's back going up at 0 would be right here. So that, if it's a little more than 3, I'm thinking that's probably 1 pi, right? And sure enough, it is. So when I multiply by 2, the period is now 1 pi. So I've taken my 2 pi period from here, and since I multiplied that by 2, I actually ended up dividing this period, and now I have just pi for this period, which is, we've done that before. It's shrinking, right? It's compressing. So does it affect the amplitude at all? Is the maximum still 1 and the minimum still 1? Sure. So this has no effect on the amplitude. And then, are the domain and range affected? Well, it's still going on and on forever. So no, those aren't affected. And it's still, since the amplitude's not affected, the range wouldn't be affected. And how about the midline? No, I haven't shifted it up or down. So this is no change here. So we call this a horizontal compression, and I think it makes a lot of sense when you're looking at a wave. Shrinking it together, it definitely is compressing it horizontally. Now we're going to do something different, and I want you to try this one and then come back. You can look at the graph and see that the period doesn't change. It's still 2 pi. So the period is still 2 pi for both of them. This time, what's changing, because I'm multiplying the output by 2, I'm changing whatever goes in the y direction. So that would change my amplitude. So the amplitude is now 2 times higher. So it used to be at 1, and now it's at 2. The domain and range aren't affected, and the midline is not changed at all. If you need to, you can graph these, but I'd like you to think about it and try it without first. Think about the amplitude and the period of each of these, and then if you need to, you can graph it and see what has changed, how it affected the amplitude and the period when I did several things to it. What I did over here was I graphed the parent function cosine in the red, and I graphed the new one that I did the changes to in the blue. So this is a really rough graph. But you can see that when I multiply the x by 1/2, that means I take the original period, which was 2 pi, and I divide it by 1/2. Remember, dividing by a fraction is the same as multiplying by the reciprocal, so now you would get 4 pi. So it basically stretched it out horizontally. And then because I multiplied that whole thing, the cosine of whatever it is, by a third, I've actually shrunk it, right? It's getting closer and closer in a vertical sense. It's getting closer and closer to the x-axis, so I shrunk it vertically, compressed it vertically. Now this one ended up being kind of interesting. Since I was multiplying by the sine of pi x, I take 2 pi, divide it by the change of x. What am I doing? I'm dividing it by pi, and I end up with a period of 2. That looks a little strange on your graph, and I know this isn't very good, but you can see how it starts at, this is sine, so it starts at 0 and then goes up, down, across, and then back up again right here. And that's about 2. I know it's hard to tell from that. And I apologize for my horrible graphs. The amplitude is 2, so this amplitude was 1 here, so I tried to make it about twice as big. And yeah, with my rough sketch here, this is about twice as big down that way. So hopefully you got that. We're going to stop here and try your Math Excel, see what you can figure out about the features. I would try as much as you can without the grapher and then put it into a grapher to double check your work. Thank you so much. Have a great day.